this error propagation. And I wanted to explain this because this involves a bit of stats and whatnot. And this also includes some bootstrap. So maybe explaining this after the break would be beneficial, because this is usually one of the first questions reviewers ask if you submit a paper and they are knowledgeable enough that there's the uncertainty related to your offsets. And then you should be able to tell, well, it's negligible, we tested, or you should be able to address that concern. And this is one way of doing that. So I think this is going to be important. And then model validation is maybe something I can quickly do right now, because I'm not really doing the model validation per se, because there are many different ways of doing that. I just wanted to highlight that so far when we looked at a prediction, we wanted to predict how D varies as a function of deciduous forest. When you want to compare your prediction to your observations, you need to add in the offsets. So what's here is that now this lambda, your expected count, is going to be D times A times B times Q, as we saw before. So if you want to compare your estimate to this mean count, so the observed values, you need the prediction for density, and you need to multiply that together with the correction, which is e to the power offset. So for this two cases of GLM, null model and deciduous forest, this is how you would calculate the mean. Same prediction as we had before, times e to the power offset. You already have that calculated, so you can just either add it to this one and exponentiate after, or once you exponentiated this to get capital D, then you can multiply that together with the correction, which is e to the power offset. Same for the intercept, and I'm just using one column from capital X. Here we have two columns, two coefficients. So this is how we get lam naught and lam 1. So now we can look at the plots. This is another box plot that I find really useful. Look at the null model. There is no relationship between our predictions and the observed counts, which is expected. We haven't incorporated anything in the model yet. It shouldn't make much sense. However, if we have a meaningful model, then if we look at a box plot of observed counts versus predictions, we would expect the mean to increase. And as we run out of higher counts, that might break down a bit. But here, when we have zeros and ones and twos for sure, we should see an expected pattern. If we could capture relative abundance well in our model, then this should increase. And that's exactly what we see. So that's reassuring. Now, you would use this lambda and your observation to do some goodness of fit. Am I getting the same amount of ones and twos or whatnot as I would expect based on Poisson? Or you can just say, I want to look at my zeros and ones, and I want to be able to fit some kind of receiver operating characteristic curve to calculate area under the curve. That's another common metric, although it's not perfectly suited for count data, but people still do it quite often. And when you want to do that, again, you need to use this lambda, which includes the offset. And there are many packages to calculate this. I just found it often quicker to implement my own, and this is what you can see here. We get the rock curve. Based on that, we calculate AUC. So this is our AUC for the null model, pretty dismal. We would expect 0.5 if the model captures nothing. So anything beyond 0.5 is considered good or increasingly better. Close to 0.8, that's really good according to some standards. So around 0.6, 0.7, you would probably say, well, that's a good enough model. And this is 0.8, which makes it a really good model. And then you can also plot the rock curves, which is false positive rate against true positive rate. Black is the null model, below this diagonal, really bad. Deciduous forest, really good. So this is how you would do some kind of goodness of fit testing or model validation. You need to make a prediction that includes the offsets. And that is going to be one of the reasons I don't propagate the errors through my modeling, is because when I want to do validation, it becomes really complex, and you will see why.